In this lecture, we'll describe how to invert an n by n matrix. First, remember that not all matrices are invertible. A matrix is invertible if its row equivalent to the identity matrix, or if its reduced row echelon form is the identity matrix. So let's say that A is an invertible matrix, and we would like to find its inverse. Well, if it's invertible, then we know it's row equivalent to the identity matrix. That means that I can always find a sequence of elementary row operations such that when they're applied to A, it will give me the identity matrix. So let's say that I need P of those elementary row operations. And let's call the elementary matrices that we need to transform A into I, E1 through EP. That means that EP times EP minus 1 times EP minus 2 times and so on, all the way to E1 times A. If I apply all these elementary row operations, I end up with the identity matrix. If that's the case, then the inverse of A is simply given by the product of these elementary matrices. EP multiplied by ... multiplied by E1. This is very simple to show. If A is invertible, then I know that A times A inverse is equal to the identity matrix. Now multiply both sides by EP times all the way to E1 times A inverse is EP times E1 times the identity matrix. Since the elementary matrices EP through E1 are such that this becomes the identity matrix, we see that we have I times A inverse is equal to, and on the right hand side we can remove the last I because E1 times I is just E1, so we have EP times E1. And finally, pre-multiplying by the identity matrix makes no difference, so we have this result. So here's the formula for how to invert the matrix. Simply find the elementary matrices that transform A into I, take the product of those, and that is the inverse of A. Let's illustrate this with a simple example. Here is a 2 by 2 matrix. I yet don't know if it's invertible. The way to find out if it's invertible, at least at this point where we have not discussed determinants yet, is to transform the matrix into its reduced row echelon form, keeping track of which elementary matrices I use. First, I want to get rid of the 7 using this elementary matrix. Then I'm left with this. Next, I want to get rid of the 9 using this elementary pivot matrix. That leaves me with this matrix, which is now diagonal. Next, I want to scale the 8 and make that into a 1. So then I use this scale matrix. So now I have only one step left, and that's to scale the 2,2. And to do that, I use this scale matrix. Now A4 should be the identity matrix, and it is. So we know that the matrix we started with, this one up here, it is invertible because it's row equivalent to I. And we can now also find its inverse. All we have to do is to do the product of these 4 elementary matrices. It's important to do it in the right order because remember, matrix multiplication is not commutative. So this should be the inverse of A. Let's double check that by asking R to find the inverse, and hopefully R will come up with the same answer. Okay, so in practice, you very rarely invert matrices by hand. This result is important mostly for theoretical reasons. It allows us to write the inverse of a matrix as a product of elementary matrices, and that will turn out to be very useful for understanding more advanced concepts in linear algebra. But if you do need to invert a matrix, there is a much more efficient way of doing that than to keep track of the elementary matrices and take the product of them at the end. And that's simply due to this fact. We notice that precisely the same elementary row operations that transform A into I, that is E1 through EP, applying exactly the same row operations on the identity matrix will transform the identity matrix into the inverse. So this fact we can utilize to find the inverse much more efficiently. What we do is we create a fake matrix called B. This fake matrix is constructed by first putting A to the left, and to the right of A we put the identity matrix. In R, for example, you can do that using the cbind function. So I have my A matrix and I have my 2 by 2 identity matrix, and I would like to create a matrix B which has A to the left and the identity matrix to the right. Then you just do B cbind to the left, A to the right, diag 2 like this, and this will create my B matrix. The idea then is to create the reduced row echelon form of B that will do exactly the same row operations on the identity matrix which is on the right. The identity matrix will just simply follow along the right and be transformed into the A inverse at the same time that A is transformed into I. So all we have to do now is reduced row echelon form of B. That will give me the identity matrix to the left and the inverse of A to the right. So again, we have the inverse here in columns 3 and 4. Note that you can follow this procedure for any matrix A, whether it's invertible or not. Just create your B matrix with A to the left and I to the right, do the reduced row echelon form of B, and check the left-hand part. If the left-hand part has become the identity matrix, then you know that A is invertible. If the left-hand part is not the identity matrix, A is not invertible, and the right-hand side of the reduced row echelon form has no meaning. For example, here's a matrix A. I create my B matrix like this. I do my reduced row echelon form of B, and I see that the left-hand side here is not the identity matrix. Then I know that A is not invertible, and this is by no means the inverse of A. So to review, Gauss-Jordan elimination on this fake matrix B will kill two flies with one swat. A goes into IN, the same elementary row operations are applied to IN, and IN will go into the inverse. And this will always work as long as A is invertible. There is, in general, no useful formula for the inverse of a matrix, with the exception of the 2 by 2 case. And this case is so common that it's really useful to memorize what the inverse of a 2 by 2 matrix is. So let's say that A is just an arbitrary 2 by 2 matrix with element A, B, C, and D, where A, B, C, and D can be any numbers. In that case, this matrix is invertible if and only if AD minus CB is different from 0. The way to prove it is simply to check when A is row equivalent to I. If it's invertible, then the inverse is given by this formula. In front of the matrix, you have the inverse of this non-zero term, AD minus CB. And for the matrix elements, note that the diagonal elements have swap places, and you have a minus sign in front of the non-diagonal elements. A formula which is worth memorizing. Unfortunately, no such simple formula exists for the 3 by 3 case. All you have to do to prove this result is to do the Gauss-Jordan elimination on this matrix, and you will discover that the reduced row echelon form will be the identity matrix if and only if AD minus CB is different from 0, and if AD minus CB is 0, the reduced row echelon form of A will not be the identity matrix and A will not be invertible. When you're done and the matrix is invertible, you end up with, on the right hand side, precisely this inverse displayed here in the second bullet. You should try to do that, and if you get stuck, check out the exercise a little bit later on. Let's double check the formula with the example we considered previously. So here A is 8, B is 9, C is 7, and D is 6. AD minus BC is equal to 48 minus 63, which is minus 15, and that's not 0, so we know that A is invertible. So then the inverse is given by 1 over minus 15. Swap the diagonal elements, we get 6 here and 8 here. Put minus signs in front of the non-diagonal elements. So this is the result. So let's check this. This is the inverse that we found. And compare that to the inverse of A. We see that the formula checks, at least for this example. And if we would like to triple check, we can do that as well and see that, except for rounding errors, the product of A and the inverse is the identity matrix.